Alright, here is Fluid Dynamics Part 1 where we talk about pressure. So before we talk about units and typical values, let's look at the definition. So the definition of pressure is force per area. You've probably used this word, right? It has in different contexts like, oh, I can't stand the pressure of creating a video lesson. But in physics we talk about force per area, and let's look at an example before we talk about anything. So I know I like to drop masses onto my hand or whatever. So here we have our typical 1 kilogram mass, weighs 2.2 pounds. And in our first example over here, what I'm going to do is I'm merely going to support this mass by my hand. Okay, so what I'm drawing here is the area that the mass has in contact with my hand, and so there's 2.2 pounds of force pushing down on my hand in that region. And it's no big deal. I do this every day in class. I can support the mass and it doesn't hurt or anything like that. And in the second example, we're going to take that 1 kilogram mass and we're going to glue a needle to the bottom. Don't ask me why we're doing it, but that's what we're doing. We're gluing a needle to the bottom of the mass, and I'm going to support that mass on my hand. Ouch. So in red, that's like the drop of blood, right? Because this needle is definitely going to pierce my skin. It's going to hurt. I'm going to scream and cry and all that good stuff. But the reality is that it's the same force. It's just 2.2 pounds. So yeah, I'm just supporting 2.2 pounds, but I'm supporting that 2.2 pounds over a smaller area. And so if we look at the formula version of pressure, so we have 2.2 pounds of force, and if this number here is large, so a pretty big area, then this is small, and it's a small amount of pressure. If this is small, right, dividing by a small number makes something very large, so a small area means it's a very large pressure. So lots of pressure, not a lot of pressure, but it's the exact same force that I'm supplying. Alright, so maybe that gives you an idea of what we're talking about by pressure. Let's look at some typical values here. So pressure in car tires, this is about 35 psi is what your tires probably say. Sometimes if you have snow tires, they're supposed to be at a higher pressure, which sort of at the microscopic level gives the little sipes in the tires more traction in the snow. Pressure in bike tires, if you're into mountain biking, sometimes people are running their pressure pretty low, so 10 psi, whereas in a road bike with those little skinny tires, it's usually more like 90. Sometimes if you're racing or whatever, even 110 psi. That's probably what they'll say. And so by psi, we're talking about pounds per square inch. So pounds per square inch. And I don't know what kind of a screen you're watching this on, but as I'm drawing it, this is about a square inch. So when we think about 35 psi, 35 pounds, that would be, I don't know, maybe 10 textbooks or something. Imagine supporting them by this on this little area, right? That would be kind of difficult. Just to give you a sense of what 35 psi means. Blood pressure. Typical, I used to have high blood pressure. Mine was 140 over 90, which is not so good. It's not terrible, but yeah, that wasn't good. So a standard or a good value for someone like me would be 120 over 80. If you're young or very light, you might have lower blood pressure. But we know this is the systolic over diastolic. So when your heart is pumping, that's the pressure in your arteries, and when it's at rest, so in between beats, that's the pressure in your arteries. And the units here, that's not psi. That would be pretty intense. This is millimeters of mercury. And so on the next page, I'll show you what a barometer looks like and how this was sort of the first way that pressure was actually measured, or one of the first ways. So we'll talk about a barometer here soon. And atmospheric pressure, you may have in mind 14.7 psi. That's a number that might come to mind, or 760 millimeters of mercury. So this is sort of standard temperature pressure, so at sea level. This is the air pressure, and we'll talk about what that means. In Mammoth, So, no, let's just talk about that, what that means right now. So, what this means is if you look at the square inch, and if you were to zoom way, way out, so we're going to look at this little column of air that goes way up into the atmosphere. So we're zooming way, way out. Here's the Earth. We've zoomed way, 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 way out. And we're looking at, so let's say the atmosphere reaches out here. That's not drawn to scale, but in here there's all these gas molecules, and we're looking at this little column of air sitting on this 1 inch that's maybe on your hand or something. If we were to add up the weight of all those gas molecules, it would weigh 14.7 pounds. So that's what we mean by air pressure. And it's actually quite a lot. Oh gosh, let's get those guys out of there. We'll do some calculations where we look at air pressure, and it's amazing how many pounds it actually is for a certain area. In Mammoth, because we're higher up, there are less gas molecules sitting on top of us. So the air pressure in Mammoth at, this is our elevation, approximately 7,500 feet, the air pressure in Mammoth is about 11.1 psi, or let's see, do we know what that is? Oh, I've got it in kilopascals, so we'll talk about that in a second. But anyway, so there is definitely a difference, all right? About 25% less air pressure up here, which means less oxygen, which is why when people come up from sea level, they're, it's hard for them to breathe. I like that when I go bike riding with them. And as a little side note, we always talk about 9.8 meters per second squared as being the acceleration due to gravity. So the farther you are away from Earth, the less this is. And technically, we are farther away from the center of Earth than somebody at sea level. So it turns out that the acceleration due to gravity for us up here is actually more like 9.7, I looked this up, 9.783 meters per second squared. We could calculate this, but that's definitely not a 25% decrease. It's something like a 0.17% decrease. So yeah, acceleration due to gravity is a little bit less, but there's a huge difference in air pressure between here and sea level. Okay, so the units that we use, we're all about MKS, meters, kilograms, seconds, and newtons in physics. So a newton per square meter, which would be a very low pressure, this is defined as a Pascal, PA for Pascal, and it's so little that we normally use kilopascals, but this is our fundamental unit when we talk about pressure. So when we're looking at atmospheric pressure, so 760 millimeters of mercury is the same thing as 14.7 pounds per square inch, which is the same thing as 101 kilopascals. So 101,000 pascals. These are very small units of pressure. So this is what we use. Definitely get that in your notes. These will be helpful conversions between these units. Okay, so let's move on to the next page and take a look. Let's see, we have a question here. How much pressure does the typical automobile exert on the road? So there are definitely some unknowns there, but we can figure it out. So the average weight of a car, in your head you're probably guessing, and I was guessing 3,000 pounds. But I looked it up, and we're going to use, so this was in 2012, the Environmental Protection Agency did a study, and this was the average weight of a car in the United States. So that's the average weight of the car. It's being supported by 4 tires, and when you think about the tire on the road, right, the tires bulge out a little bit. There's going to be a little, these are the treads, right, and this is the tire. This is a 3D view. It's kind of working. And you can picture this is the contact, the footprint of where the tire touches the road. So I was guessing that was about kind of an ellipse, about 8 inches wide, right? And if it's elliptical, that might be similar to a circle that's about 6 inches in diameter. So when I was creating these notes, I was thinking through and just kind of solving this out, and was really surprised by the result. So we have this much force, and it's exerted over this much area times 4. So if we were calculating this area, that's 3 inches for our radius. And so what do we have? We have force per area. And so 3977, right, pounds per, and our area is 4 of these. So we have pi r squared, and then times 4. And I plugged this all into the calculator, and I got 35. I had a good chuckle. It was cool. 35 pounds per square inch, which is exactly what your car tires will say on the side as the recommended pressure. So, and I was just making up this example and looked this up and was guesstimating here, but was kind of blown away at how close that value was. So this is sort of an example of what they're called Fermi questions, where they're good estimates in situations where very little information is known. And this was not an estimate. I looked that up. If I had used 3,000 pounds, I would have got a different value. But let's take a look at this next page before we run out of time. So here's an image of a barometer. This is what's his name? Evangelista Torricelli, and he's got a cool mustache. But he's the guy who invented the barometer. These are images of old barometers and what they actually look like. So these are designed to measure air pressure. This diagram does a good job of explaining what's going on. So there's a vacuum inside here. There's no air pressure, right? Air pressure is pushing down, and it pushes up, and mercury was used because it's liquid, but it's really heavy, right? They built one of these out of water, and it had to be as tall as a building, so it was very cumbersome. You couldn't take it around with you, and it would break and stuff. So anyway, there's a vacuum in here, and the mercury being heavy, the pressure pushes this up. So it's like the weight of this pushes down, right, and balances out given the air pressure. So this is how air pressure was measured originally, and 760 millimeters. That's 76 centimeters, which is about the height of your desk, right? It's less than a meter. So the mercury would rise that much, and that's a measure of how much pressure the atmosphere is pushing down. I think we have time for one calculation here. So practice with calculations. Atmospheric pressure at sea level is 101 kilopascals. How much force does the air exert on a school desk? That is 80 centimeters wide and 60 centimeters long. So here's our school desk. We have 0.8 meters, we have 0.6 meters, and there's some air pressure, and what we're looking for is force. So if we substitute in, we know that air pressure is this many pascals. That's a lot. And we're looking for force, and the area of the desk is 0.8 times 0.6. And so I worked this out beforehand. I multiplied these, and I got force is 48,480 newtons. That's a lot. If you remember, a newton, about 5 newtons, is equal to a pound. So this turns out to be about 9,700 pounds. And you think, well, how come my desk isn't being crushed by all those air molecules sitting on top of it? Right? This column going up to the top of the atmosphere, and all these air molecules are weighing on the desk. Well, the air is kind of free to move, very free to move. So there's actually air pressure underneath the desk as well, and it balances out. But we do have this much pressure sort of, pushing in on us. And luckily we're not crushed because our internal what am I trying to say? Our blood pressure and the fact that our bodies are made out of fluid mostly helps to balance that out. Yeah.